In this lecture, we discuss the Fourier method to find the formula for the solution of the heat equation satisfying given boundary conditions. So, again let me begin with the statement of the problem. So, this is heat equation. So, now we are working in a finite interval. So, x is in L is some positive number and t bigger than 0. So, initial condition is given. So, before prescribing the boundary conditions at x equal to 0 and x equal to L, so let us begin with the procedure for this Fourier method or separation of variables. So, in this method the solution is sought in this form, namely x(x). So, this is what we did even while obtaining the solutions for the heat equation in the entire line, entire real line. Okay, this is what we started with. Then you plug in this expression in the heat equation and you obtain T prime by A square T is equal to x prime by x, and again as we discussed there, this is a function of t only and this is a function of x only, it must be a constant. And for physical reasoning we again take negative sign where lambda is positive. And by the by, so we are seeking non trivial solutions. So, that means this both the functions are not identically 0, but then this is just a 0 solution and it may not satisfy the initial condition. So, whatever boundary conditions we put at x equal to 0 and x equal to L, they transform into boundary conditions for the function x. Okay. So, if we take positive sign, again let me repeat that, if we take positive sign, that produces an exponentially growing t which is physically not acceptable. So, we reject that the positive signs and consider only negative sign. So, in that case we immediately get that t of t some constant. So, let me write C1 C exponential minus a square lambda square t, and for x we have so these will be the common features for all the boundary conditions we consider, and we have to only see which boundary conditions give us non-trivial solutions. That is important for us. Okay. So, for all the things this will be the common things. Only thing is we have to determine the values of those lambda for which we get non-trivial solution. So, this is certainly non-trivial solution for t all the time. If we take c not equal to 0, but here since x has to satisfy appropriate boundary conditions, the choice of C1, C2, at least one of them non-zero, is possible or not, we have to see case by case. So, first we begin with simple boundary condition, zero Dirichlet boundary condition. Namely u of 0 t is equal to u of L t is 0 for all t positive. So, let us begin with this boundary condition, and these two boundary conditions transform into the boundary condition for x. So, we get x 0 equal to x L equal to 0. So, if you put, so remember, just let me write that x x is C1 x, C1 cos lambda x and C2 sin lambda x. So, if I put x equal to 0, cos is 1, sin is 0, that implies C1 is 0. So, x 0 equal to 0 implies C1 equal to 0, and then x x becomes just C2 sin lambda x. The other boundary condition, namely x L equal to 0, implies C2 sin lambda L is 0. So, if you take C2 equal to 0, then x is identically 0, we are not interested in the trivial solution. So, for C2 non-zero, this sin lambda L should be 0, and that implies, so lambda cannot be arbitrary. So, lambda L just n pi L, n pi, and if we cannot again take lambda equal to 0. So, this is n equal to 1, 2, etc. So, in that case we obtain, so there is a discrete set of lambda n. So, call it lambda n. So, lambda put lambda n is equal to n pi by L, n equal to. So, this is general feature of the method. So, this, in order to find the non-trivial solutions, the lambdas will form only a discrete set, and in this particular example we have seen that discrete set is given by n pi by L, and then the corresponding solutions. So, we write it. So, T n t, some constant C n exponential minus n square pi square a square t by L square and x n x. So, since we are multiplying t and x, so that constant will not write here. So, we will just write simply sin n pi by L x. So, again by linear superposition principle, so we obtain a solution. This is formally. So, just sum them. U x t is equal to summation n equal to 0 to infinity, n equal to 1 to infinity, not 0, C n exponential, let me write it again, sin n pi by L x. So, we need to determine these constants, and constants will be determined by using the prescribed initial condition. So, we have g of x is equal to u x 0. So, simply substituting t equal to 0 in the infinite series, get C n So, this means the requirement on G is that it is expressed as a Fourier sine series which is convergent at all the points in that interval 0 n, and this is provided by the Dirichlet theorem in the theory of Fourier series. So, we take minimum requirement on G, namely, so if G 0 is equal to G L equal to 0. So, if G vanishes at the end points and G is C 1 except at a finite number of points. So, more precisely we can take piecewise C 1. So, this is Dirichlet theorem from the theory of Fourier series. So, then G is expressed as Fourier sine series, and the series is convergent to G x. So, in general Fourier series you can always form, but that may not converge to the function. So, there are some conditions required, and Dirichlet theorem provides these are sufficient conditions for the convergence of this infinite series, sine series, where G n are the Fourier coefficients of G, where G n 2 by L 0 to L G x sine So, we take C n equal to G n, and with this hypothesis on G, then finally we obtain the solution. So, therefore, the solution is given by, I should not call it solution yet, because we need to verify it is a solution. Solution is given by u of x t is summation n equal to 1 to infinity g n exponential n square pi square a square t by L square sin n pi by L x, where g n's are the Fourier sine coefficients of the function g. Okay. So, with the stated hypothesis on g, that is always possible. So, we do get this infinite series involving sine function and exponential function. So, what we still need to do is that u is, we need to show u is u t u x x exist and are continuous. So, when u given by this infinite series, the only way to check for the existence of these derivatives is again rely on the term by term differentiation, and in this case this exponential term saves us. So, there is absolutely no difficulty in differentiating this infinite series term by term, both with respect to t as well as with respect to x, and the reason for that is okay, term by term differentiation both with respect to x and t is possible for the following reason. So, let me write it separately. So, once we see in one particular case, so if you just remember that, so it smoothly goes through in other cases also. So, look at this terms in the infinite series. Suppose I differentiate with respect to t, I get an n square factor, and if I differentiate with respect to x 2 times, again I get an n square factor. Okay. So, somehow that n square factor has to be tackled, and in fact more generally we have n to the k exponential minus n square pi square a square t. So, you consider this sequence as n varies is bounded for any t. So, whatever the terms come there, term by term differentiation, I can always make some big factor of n in the denominator, so that the series converges, and then you are justifying term by term differentiation with both with respect to x and t. So, you simply do without any problem because of this observation. And once we do term by term differentiation, so we already seen that this is solution of the heat equation. So, if you do one differentiation with respect to what t one time and differentiation of the sine term 2 times. So, each of these terms satisfy heat equation, so is the sum. So, there is absolutely no problem in doing term by term differentiation. So, therefore, u is the required. So, we already seen the uniqueness, and so this is the only solution of the problem, required solution of the said problem, stated problem. So, this is an initial boundary value problem. Okay. So, we took the 0 Dirichlet boundary conditions here. Physically, we say that the thin rod is insulated at both the ends. So, this we can replace by some prescribed. So, this is another. So, we can prescribe, this is very simple. The boundary conditions u0 t equal to u1 ult equal to u2. So, u1 and u2 are constants, that means the end points of the rod are maintained at some fixed temperature. So, this is not a difficult problem at all. What you do is, we already have the solution with 0 boundary conditions, and for that you just add one term. Okay. This requires again by linearity. Linearity is very important. This requires adding the term so what term you add? So at x equal to 0 I want it to be u1. So you add 1 x by L u1, and at L I want it to be u2. So this is just x by L u2. So this function satisfies the boundary conditions, and since it is only a function linear function of x, so obviously it satisfies the heat equation. You just add this term to the solution, to the above solution, u. And then you get the formula for the solution of this prescribed boundary conditions may be non-zero. Okay. So this is a simple observation. So let us take one more, but in this case we will not get explicit formula for the lambda n's. So consider the boundary conditions. And this now requires the Sturm-Liouville theory from ordinary differential equations for the existence of solutions and the orthogonality conditions, etc. So, I will briefly discuss this one and maybe provide some notes later. So, these boundary conditions u x at 0 t minus h u 0 t equal to 0 and u x L t plus h u L t equal to 0. So, here h is a constant, non-negative constant. Okay. Physically, this is referred to as free exchange of heat at the end points. So, this u sub x, that first derivative, refers to the flow of heat across the boundary points, exchange of heat at the boundary points. So, now again recall this x s is C 1 cosine lambda x, C 2 sin lambda x. So, these boundary conditions transform to boundary condition for x at 0 and L. So, that means we have x prime 0 minus h x 0 equal to 0 and x prime L minus H XL equal to 0. Now, you write down these two conditions in terms of C1 and C2 that requires little algebra. So, let me write that. So, you have minus HC1 plus lambda C2 equal to 0, and another one big expression minus lambda sin lambda L plus H cos lambda L C1 plus lambda cos lambda L plus H sin lambda L C2 is 0. So, we have to determine C1 and C2, and we have got two equations. Okay. What we want is not both C1 C2 0. So, this is a requirement because we want x to be, because x is not identically 0. And now, we have two systems of two equations for C1 and C2, the linear equation, and if you want, so these are homogeneous equations, but we want C1 C2 to be non-zero solution. So, that implies the determinant of the coefficient matrix must be 0. Determinant of the coefficient matrix should be 0 in this system. And if you write down that, so that this gives, so you already see some complication and these things are not explicit. So, 2H cos lambda L. So, you just compute the determinant and simplify it, equate it to 0, and you get so when H is 0, it is very simple. So, H is 0, this the left hand side is not there, though then again we get lambda sin lambda L equal to 0, and the lambdas are easily given. But when H is positive, we can only show there are infinitely many lambda n, and they tend to infinity, satisfying the above equation. So, it is not possible to write down what exactly lambda n is, but you can geometrically show there are infinitely many lambda n, they are tending to infinity, satisfying this equation. And then again as usual, now again this x n and T n is known, but lambda n is not explicitly known. T n is again no problem. So, you call it C n exponential minus lambda n a square t by L square, maybe a pi is missing, okay. But x n is again, now it will involve both cosine lambda n x and sin lambda n, linear combination of both. and now this time we cannot determine this lambda n explicitly, but we can still show that actions they form an orthonormal family, and any reasonable G can be written as Fourier series with respect to this action, and finally we obtain a solution. That requires little more computation, and that will provide in the notes how these lambda n's can be obtained geometrically, and though the formula is not explicit because of this lambda n's, but nevertheless the procedure is the same, and we do obtain again the solution in the form of an infinite series. Again there is absolutely no problem with regard to verification of term by term differentiation, both with respect to both t and x variables, and we do obtain solution of the stated boundary value problem. So, with that we come to an end of this discussion on heat equation. So, whatever is missing, those things will be provided in the notes. Thank you.